we've been going over different techniques on how to integrate. So first we looked at U substitution, which allows us to integrate things where like we have stuff inside of stuff. Okay. Then next up we looked at our natural arcs, which was started having like more fraction type stuff, which then gave us our long division. So when I have a fraction where remember the numerator is bigger than the denominator, I can do my long division first. And then lastly, we're going to integrate with inverse trig functions, or our answers are going to have inverse trig functions, along with, so just like our ln kind of pairs with our long division, our inverse trig functions pair with completing the square. Okay? And that will be the last, basically, technique that we learn to integrate. Then the next 2 units that we will do is basically like applications of integration. So now that we've learned how to integrate all of these things, what does that allow us to do? So what can we do with integration? So we looked on Friday a little bit at reminding ourselves of what our tangent inverse was. Okay. But today we're going to look at both tangent inverse and sine inverse. Technically there's cosine inverse as well. But remember, the derivative of cosine inverse just ends up being negative of the derivative of sine inverse. So instead of memorizing another thing, basically we'll just take out the negative and make it negative sine inverse instead. So we kind of just ignore cosine inverse, which means one less equation formula that we have to memorize. So do we remember what our derivative of sine inverse is? Remember, the derivative of what our sine inverse is means that if I take the integral of that, I will get sine inverse. So can you go back? Yes, no, maybe.
Square 1 plus x squared?
Almost.
1 minus x squared?
There you go. So usually it's 1 minus x squared. Okay? But because we're working our way backwards, alright, we are not always just going to have a 1 here. So instead, we're just going to put it as an a squared. So as long as a is just a constant, as long as it's just something squared, we can still take the antiderivative and we will get a sine inverse. So it's going to be sine inverse of x divided by a plus c. Now, sometimes it might be 1, and in that case, this will just be x, and we don't have to worry about it. Then we talked about on Friday, remember that our antiderivative of tangent inverse is 1 divided by yes. But again, I'm going to use an a squared. So instead of 1, a squared plus x squared equals 1 divided by a times tangent inverse of x divided by a. So if you're wondering what ends up happening here is because I have a square root and it's on the bottom, okay, my square root and my a end up reducing out, which is why I don't have a 1 over a in my final answer key. However, on my other one, I don't have a square root to like help reduce things out, which is why I end up with a 1 over a on the front of my tangent. Are we all okay with that? To me, it takes more time to like show you why that works the way it does, and it's kind of confusing because you end up having to like factor things out and reduce things and take square roots of the things that it goes away because the square root's there. All right. And like I said, technically negative of the square root would be cosine inverse, but instead of that, we can just factor our negative out and then just make it negative sine inverse. So that's why we don't have cosine inverse. So let's look at an example. What we got here?
Sine inverse?
It will be. 1, can you tell me what our a value is going to be?
2.
And then from there, I don't really have to do anything else. That is just our formula. So I just have arc sine of x divided by 2 plus c.
So what did you plus and minus to? Is this taking the square root of 4? Or does it just cancel out?
Well, because I don't have a, so like I'm not taking the square root of that thing because I can't take the square root of my 4 and my negative x squared separately because I have subtraction there. It would have to be 4 minus. And also I only put a plus or minus when I am adding in a square root to an equation. So like if I'm square rooting both sides of an equation to solve for it, I'm going backwards, and so it would have had to be. Does that make sense? So I don't have to in this case. Because also remember that like when we take the square roots of x squared, right, we end up taking the absolute value in order to bring those things out. So we would take the absolute value of the negative 2 at the end. So it would end up being positive anyway. Because the square roots are equal. Okay, someone from group 4. What's different about this one? Oh, it has a 25. Okay. Is that 25 special though? Is there a way we can rewrite 25?
Times squared.
Yeah. So my a value is still going to be 2, but now we also have to rewrite our x as 5x quantity squared. So someone from group 3, what am I going to have to do in order to be able to integrate?
Would you have to use them?
We do. We have to use of this. Now, I don't want to make the whole thing my u, right? Because this almost looks like our normal equation, yes? I only need to u sub the part that's on the inside, which in this case is just this part that's being squared. So then what is our du?
5 dx.
Okay? Do I have an extra 5? No. So now, does that look like our formula from the first page? Yeah. And then again, because this is a indefinite interval, I'm gonna plug my x's back in. questions on that? Group 6, what does this one look like it's gonna be?
Tangent inverse.
Yeah, we don't have a square root this time, so it is going to be a tangent inverse. But I do still need to rewrite a little bit. What's our a value gonna be?
3.
And remember that we do not have a square root here. So I do end up with a 1/3 on the front side. Root 4, which one do I plug in first? Those are your two options, yeah. So we plug in the top or the bottom first?
The top.
We plug in the top first, agreed. So plugging in 3 first, 3 divided by 3 gives me 1. So then I am subtracting. Plugging in square root of 3. Have I evaluated that function?
Yes.
Yeah. Do I need to continue on if it's a free response question? No, especially as bad as some of y'all are at our unit circle. Okay, however, multiple choice questions, they are probably going to evaluate those. Both of those are on our unit circles, so like this would be fair game for a non-calculator question. So, we should all be able to get here. This is the calculus stuff. The next step is our pre-calc stuff. But if we're given a list of multiple choice answers, hopefully then that we can help us match and remember which thing goes with what. Yes? But, as a side note, remember that tangent is equal to sine over cosine. Yes? So the only way that I could get 1 out, and this is the inverse, right? So we're going backwards. We're trying to figure out what theta or angle would give me 1 for tangent. And so the only way that a fraction can be 1 is if the top and the bottom are equivalent. And so which one of our angles is the top and the bottom equal for sine and cosine? 45 or pi over 4. On the AP test, any answer that involves an inverse trig function is going to be given to you in radian for multiple choice questions. If you wrote it as degrees on an answer for an FRQ, 1, you shouldn't be evaluating it, so don't write degrees. But 2, if you did, it would still be right. But it is going to be given in radians on a multiple choice. Now, here's the fun one. Okay, so remember that tangent is sine over cosine, yes? When we get tangent, okay, remember that our 2 other options are going to be pi over 3 or pi over 6. Okay. Our 2 options for tangent are just the square root of 3 or a 1 over the square root of 3. Which 1 over the square root of 3 is what gives me square root of 3 over 3 because it's been rationalized. Yes? Okay. So if I have a 1 over the square root of 3, right, that means that my square root of 3 would have needed to be in the bottom. So that means that cosine would have to be a square root of 3 over 2. So which one of these on our unit circle has a square root of 3 over 2 for my x value? Pi over 6.
Yeah.
is why I do 1/2 divided by square root of 3 over 2, which is why our 2's reduce, and we get a square root of 3 in the bottom. So this would become pi over 12 minus pi over 18. And we leave it like that. But like I said, most of us, we should stop here for an FRQ. This would be a multiple choice type answer. Questions on that? So speaking about going backwards to our pre-calc stuff. Next up, we have to remember completing the square. Yay! Because remember, notice that unlike all of these, right, we've wanted to rewrite this as something squared. Or even our one that was a 25x, I needed to rewrite that as something, my 5x quantity squared. So in order to use our inverse trig functions, we have to have perfect squares. Okay. The constant here at the end isn't that big of an issue. Alright, it's that extra x in the middle that causes us to have more issues. And so we need to make that into a perfect square, and so we do that by completing the square. So, remember that our first step is that our a value has to be 1, which is your leading coefficient. So right now, what's my a value?
4.
So we're going to factor out a 4. But again, I said the constant is really not that big a deal. So we just factor out that a value from our first two terms. And then we leave the plus 5 by itself. Next up, we are going to add in b divided by 2 quantity squared. So in this case, our new b is -2. -2 divided by 2 gives us a -1. Squared gives us a 1. But what I add to the inside, I must also balance out. Because I can't just add something because I feel like it, right? That gives us a new expression, which is not what we want. We want, especially because I have equal signs here, we want these expressions to be equivalent. But what's the one thing that we are allowed to add that doesn't change the value of an expression? If I have $5, and I want to make sure, even if I added something, I still have $5. Well, what if I had added? There's only one number. Huh? 0. Yeah, if I had $0, I still have $5. Yes? Right? But also, let's say if I got $1, but then I spent $1, did I technically add $0? If I added $1 and then spent $1?
Yeah.
Yeah, right? So adding something and subtracting the same thing still gets me 0. Okay, so I still have to add, I added a 1 on the inside, which means I have to subtract what?
1.
Almost. So remember that this 1 applies to that, this 4 applies to that 1 as well. So I didn't technically add a 1, I added a 4. So I have to subtract a 4. And then our last step, which is the whole point, is that we want to factor. And when we factor it, we should end up with a perfect square, which as long as you follow these steps, you will. So notice that we're looking at what multiplies together to give me 1, that adds together to give me a -2. And x minus 1. So we get x minus 1 quantity squared. And then now I have a plus 1 on the outside. So now notice that my x is a perfect square, which is what we want. So if that was inside of an integral, now I have a perfect square that I can use for my u for our integration. Yes, no names. Okay, let's look at an example. We'll just do one of these today, and then we'll look at some other ones tomorrow. Now remember that completing the square is not our only option, okay? Nor is it our favorite option. So if we can, we want to do u sub first. Can I do u sub on this?
Sure.
Okay, what would my u be?
X squared plus 6x plus 10.
Yeah, it would need to be the denominator. But if I make that my u, what's my du? 2x plus 6. Do I have an extra 2x plus 6 hanging out? No. So I can't use u sub. Can I use long division? No, why not? Yeah, because the top is not bigger than the bottom, so I also can't use long division. Now I have the x squared and I have a plus 10, right? So the plus 10 is not really a problem because technically the square root of 10 squared could be my a value, yes? So that's not bad, but right now I have a 6x. So we do have to get rid of that, and so that does mean we will have to complete the square. Because remember on your AP test and on my test, it's not just going to say use this to find this integral, it's just going to say integrate. So you have to choose which of the techniques that we've talked about in order to solve it. Now I am going to come over to the side and complete the square by itself, just because otherwise you have to write the integral and the fraction symbol every single time, so that's a lot of writing. So that's why I just do it separately first. I don't have an a value this time, so we don't have to factor anything out. So we just group our first two together. So what's our b value?
6.
Okay. So I have 6 divided by 2.
3.
Squared gives us
9.
9. And since I don't have an a value, since I added 9, I also need to subtract 9. And then I factor. What multiplies together to give me 9, that adds together to give me 6. 3 and 3. I get something that looks like that. Which now goes in the denominator. So next up, someone from group 1, what do I need to do in order to integrate that?
U sub?
What's my u?
Plus 3.
Ah, so then what's our du?
1.
Just 1. So do I really need a u sub? Not really. Right, like I can write that there just to be like sure, right? But I'm still going to end up with the same thing as if it was that, because I don't get anything extra, and we're all okay. Now my 8 is just an 8, it's just going to carry forward, so it's just a constant. What is our a value this time?
1.
That's nice, so I also don't have to divide by anything, so I have tangent inverse of, again, it's just going to be u, which then we would plug our x's back in, so I get x plus 3, and then I have an indefinite interval, so I get a plus c. What questions do we have there? So really, it's not super hard as long as we can remember our steps to do. Usually the hardest part when we have rationals like this, like a fraction, is just picking which technique we want to use. And then remembering the steps for whatever we choose.